That's or is that
B is the line.
A, this one?
Yeah.
Okay, and B is this one. Right? Okay.
So I think B is the center of the line, and then A is the point. So this would be,
B is the height.
this is, yeah, A is the height.
Oh,
So
A
this is
the
A1. These two dots, this is A1 for B, this is A1 for B2. And so that average is here. And then for here, it would be at this point.
Oh, right.
So that's the same
draw
point.
the line across. Right.
Did you go over this in class?
That is just to check A, right?
A. Yeah, that's for
okay.
A.
And this is B. Okay.
And then B would be this line is about here, and this line is about here. And those are different
I think he
points.
did it backwards in class.
Did he?
I think so. Didn't he say that one was A? Maybe not.
I might have missed this class.
I think
That's what I remember last year.
Maybe he had them. Maybe he had A over here, B down there in class, or something
okay.
like that. So it was like, okay, so this is.
But what you want to remember is the line. You're looking for the center of the line, average of the line, and for whatever these two endpoints are, this B or A, you're looking at where the 2 points average out to be. So another example could be.
Yeah, maybe you do like one of these weird ones.
Like one of them
Or
are
they're
parallel.
in the same
I
middle.
didn't do that one. Or this one. No,
Oh,
this
okay.
one. So this one I want to do. This is B1, B2, A1, A2.
Right.
So these points for A would be here. This A would be here. They're not
The same.
the same. So they're main effect A. B, if the lines were a good size, they would be about here, the same point. No main effect B.
Okay, that makes sense.
But interaction, because they're close.
Right.
Okay. Yeah.
And also, if the graph looked like this,
So yes for A.
would there be interaction?
Yes.
Okay. Even though they're not
Not
crossing,
parallel.
they're going to cross eventually. So yeah.
Okay. Let's do like this one of these last ones. So that would be main effect A.
The weird ones.
Yeah.
This one's got 3 levels on A.
Mhm.
And also two B's.
2 B's, yeah.
So what do you guys think about this one? Okay.
There's no main effect for B, right? Well, you have.
I know my lines aren't that great, but averaging about A here, here, and then here.
There's no
So
for
no
A.
A. And B, it's a little bit tricky because these got 3 points, but it's like around here for B1.
The average?
The average, and then around here for B2.
Mm-hmm. Right. Yeah.
How'd you get that average?
Kind of just. So it's like the 3 points of the lines are broken up, but it's kind of.
Yeah, so
hard to explain.
you could think of it in terms of like the numbers, like if this is 5 and this is 6 and this is 7. Yeah, that's not very good. Right, so the average would be about 6, right, of these 3 points.
Oh.
If it's like,
Right.
yeah. Sometimes it's helpful to put numbers to it. And then this one's 5, this one's 2, and this one's 3. It's just like
So B1
5-ish.
is up here, B2 is down here. So there isn't main effect B.
It's 6 and like 3.5 is this point. So they're different.
Is he going to put one of these on the test? One with more than. maybe.
I don't remember.
Okay.
It's not going to be more than 3 though.
It's not going to be, yeah, it won't be more complicated than like this one. So this is number, like, I don't know, the last couple graphs in the book. Yeah.
Does this make sense to everybody? Like how
you get like the averages and then like the average of the height.
we can go over it later if you want. More. Okay, so let's move on to the next one so we can hit everything on the list. Simple effects. So you start with your analysis with the omnibus F, the whole ANOVA. So I'm going to just do an example. Okay. This is B1, B2, A1, A2, A3. So omnibus, is there a difference anywhere between these cells? Okay? Between these groups. Simple effects is you want to just look at maybe one level of one of the IVs and then compare the other IV across that.
Can you say that again?
So simple effects is you're breaking it down a little bit. You want to look at a more specific effect. So that would be just looking at one level of one of the IVs, and then you're comparing the other IV across that one level.
Yeah, so like if
Like the homework assignment.
It's like the homework.
yeah, it's like the homework for this week. So it's like say you calculate your omnibus F, and then there's a difference, but it's it's basically like something is different between all of these cells and stuff. But it could be just like one cell is hugely different, and the rest are kind of like all the same. So it's really this cell that's making your omnibus F significant. So that's really the true effect, is like the effect of this cell, basically. So it's like specifying more like what's the real effect? Is it?
It's kind of like breaking down your two-way ANOVA into a one-way.
Yeah.
So going backwards from what we were doing. So the two-way is 2 IVs, and you're breaking that down to a one-way, 1 IV. This pretty much becomes non-existent when you're just looking at these 3 levels across this one factor. Does that make sense? Okay. Let me know if it doesn't, because that's important.
Why does it not become existent? I'm confused.
Well, it's not non-existent, but it doesn't factor into this analysis right here.
But aren't we looking at what B1 does to the effects of A?
I mean, well, what I mean by it becomes non-existent is like the 2 levels of the second IV, they're not important, so you're not looking at that. You're not looking at the interaction anymore. You're just looking at the simple effect.
Okay.
Right. Because the interaction includes both the levels and then all these levels. But if you want to make it a simpler analysis to find where the real effect is, this is how you start doing it. You start breaking it down to simple effects. And then even smaller is simple comparisons when you're just doing 2 groups. So I wanted to look maybe at A2 versus A3. That's a simple comparison.
We don't have to work out the problem on the test, do we?
No, you wouldn't have to do.
Okay, so just know the definition.
Yeah, I know it. Exactly.
Do we have to know comparisons? Like, Bonferroni at A-1? I had that in my notes, so I just because that would include if we went to simple comparisons.
Mm-hmm.
Right, I'm not asking that question.
No, you're right, because you mentioned at the last class that when you're doing your analysis, you're doing multiple. So you're doing your omnibus F, that's one comparison. You're doing maybe that simple effect, that's another comparison. Maybe you want to look at this one also, that's another comparison. You're breaking it down, but each one of these is a different analysis and a different effect that you're looking for. So that adds up the number of tests, and that affects your type 1 error. Is that what you're getting at? Mm-hmm. And that's where you would need to do Bonferroni corrections, Sadak-Bonferroni. If you want to do everything under the sun, you do Shepay.
Mm-hmm. Should we know that too?
Yeah, remember your post hoc test, and the number of corrections that couple allows.
Yeah, just remember, so like, it's like when we did the plan comparisons and we had, if it was, so remember A is like number of, so it's like A minus 1. So like, it's like the number of groups you have minus 1 is the number of analyses you can do. And if you go over that, then you have to correct for it. You have to correct your alpha. So you have to do post hoc test, so like a Bonferroni correction or a Chiffé. I just remember when we talked about that for the previous test. So it's the same kind of thing, except like simple comparisons and simple effects are similar to plan comparisons, except like it's almost like after your omnibus, you are like, oh wait, this is like there's a huge difference here, so I want to look at this more closely. And then you might decide you want to do like the split file thing on SPSS, where you look at just the individual cells. So yeah, so really just remember that, like, if he's like, okay, well you're doing 7 tests or something, but you only have 6 groups. So then if you have 6 groups, you're only really allowed to do 5 tests. So if you do 7 tests, then you have to correct for it, doing like the Bonferroni, which is like your alpha value over your number of comparisons.
Mm-hmm. And that would be your new alpha value that you're using to find your critical F.
So if we have 7, we just use any post hoc test, or
it depends. Remember, it depends if you're doing like the pairwise or control versus experimental.
Yeah, I remember what each test generally, especially.
Yeah.
But if we go over the comparison, then we have to figure out which post hoc tech to use, right?
Yeah.
Yeah. I mean, the main thing is correcting your alpha level. So like, you want to do your Bonferroni correction, you're correcting the level at which something's significant. So if you get a finding, instead of being significant at 0.05, it's now going to be, 0.02. So, yeah, that's the main thing.
But if your comparisons were fine, you wouldn't have to do that.
Yeah, so if you only did like 4 or 5 comparisons, then that would be okay. You wouldn't have to correct, and you could use 0.05. And if something reaches 0.05 level, then it's good to go. Mm-hmm. But if you did more than that, then you have to lower it to like 0.02 or whatever. So
you're correcting for what? Type 1 error?
Type 1.
Okay.
Yeah. And that's important to know. Remember what you're correcting for. Yeah. So, does that make sense to people? Have people done the homework yet? Because the simple effects, simple comparisons might make a little more sense if you've tried to work out the homework. Okay.
Did like half of it.
Okay. Yeah, just as long as you've kind of looked at it, because it's a little bit relevant.
Okay, so we have the analysis of marginal means. We did simple effects, simple comparisons.
Great. So that's what we did earlier with the whole thing. Yeah, and the means, not the sums. Wait, sorry, the 8s are up here. I was like, nope, means. Yeah, those are all 10. Okay.
So analysis of marginal means, you're looking for what? What kind of effects? A main effect. Exactly.
So a main effect would be if there were differences in the means.
So you're just looking at one factor. I'm looking at A. Is there a difference between the levels of A? Forget B for now. It's just A. Or the other way around. Questions? Okay. Interaction contrast.
It's kind of that thing. Yeah.
So interaction contrast is kind of your, it's kind of like a simple effect interaction. You're breaking it down. Say if you have like 3x3 ANOVA, 3 IV levels, 2 IVs, 3 levels on each side, and you want to look at a 2x2 interaction. So you're kind of breaking that down, just contrasting or comparing those 4 cells, looking at the interaction at a more specific and simpler level.
So maybe you just want to look at these.
That's the interaction contrast.
So do you need 3 levels of each IV in order to do an interaction contrast?
No, that's just an example.
Oh.
You could do a 2x2
Yeah,
and then
and
look
then
at a 1.
look at a 1.
by 2.
Which would be the same thing as a simple.
What would have to be at least 2 levels for each factor? Is that what you were asking? Yeah.
Thank you.
Yeah, at least 2 levels.
At least 2
for
levels.
each.
Sorry,
At least,
I
at least that. Yeah.
And what's the importance of it? Just like kind of like simple effects so you can see where the main effect is?
Yeah, it's just, making your analysis more specific, looking for the real effect. Another way.
There has to be at least 2 levels to do for each.
Yeah, because the
for
interaction,
IV.
you would need at least 2 levels for each IV for that to occur.
Right.
But then you could just look at like this
1.
one or something.
So it's basically the same as a simple effect. If you only have 2 levels of each IV anyway, then you're basically just doing a simple effect, right?
Yeah.
Okay.
Yeah. Which depends.
So
it's kind of
really,
down.
you're looking at the whole row.
Yeah.
So you said this with a simple comparison. You need to
Yeah,
have
that's
an
a simple
interaction.
comparison. So you need to have
That's
an
why I
interaction.
use the 3x3 example
Right.
to break it down to a 2x2.
So you wouldn't do the one way. That would be a simple effect. Right.
So you need
to have at least 2 levels of each variable,
Yeah.
like Cassandra just said.
Or if you start out with a 4x4 and you could break it down to something, a smaller interaction, a 3x3, a 2x2, but there's still at least 2 levels because you need that for interaction.
Right. So like graphically, if you had like this, and I don't know, that or something, and maybe you were just interested in looking at this one, so you just looked at that one. Does that make sense? So see, because you have like a couple different interactions going on, but maybe this is the real one that's creating the real effect. So then you just want to pare it down and look at that one.
Yeah. So you're just simplifying it.
Do we have to know anything about homogeneity of variance?
Yes. So remember homogeneity of variance. He mentioned this in lecture. I remember that if you violate that assumption, you're going to have to calculate a new error term depending on what effect you're looking at. So if homogeneity variance is violated and there's a difference between the variance here and the variance here, but I only want to look at this effect, I want to calculate a new error term for just using these cells. Because if I include everything, it's going to throw off my analysis.
Right.
It's going to account for variance that is not represented in this level of the IV.
Right, so you don't want to use the two-way analysis of variance homogeneity test for your broken down like one-way simple effects. That doesn't really make sense, right? Because you're not looking at that other portion anymore. So you just want to use what's applicable to what you're
looking. Still use a similar test like a Brown, right?
Right.
Well, that's defined if it's violated or not. Right? So how do you find homogeneity of variance if that assumption is violated? Brown's fourth side. F max.
Okay.
If you had simple enough data, maybe visual inspection. And Levine's is also in SPSS. So you look at those. Okay, is my homogeneity of variance violated? Oh, it's not. Good. I can use the omnibus F error term for everything. If it is, okay, well I need to calculate new error terms for my effects, depending on where I'm looking. Right.
This is for simple effect and interaction like all of them?
Yeah.
Yeah.
Well, it depends on where the violation occurred.
Anywhere.
Yeah.
Yeah.
So would we need to know numerically or just conceptually?
Conceptually. Just conceptually. So just, recognize that, like, your omnibus F is violated, but you just want to look at maybe this group here, then you want to calculate a new error term, because it could be that this is fine, that the homogeneity variance of this one section is going to be okay. So,
just in general, know, like, what if it's violated? What do I do?
Right.
Okay.
Yeah.
Regards
Just
to error term.
conceptually.
Do we have to know anything about orthogonality, orthogonal, like anything that's overlapping or?
I don't think that's
No,
really good.
that's more for the plan comparisons when you're doing the plus minus, the coefficients.
Okay, so nested designs. So what are nested designs used for?
Random IVs, I think. If your IV is random.
To account for random effects?
Yeah.
Yeah,
Right.
You can use, it's used to reduce within group error or variance within group variance. And examples like a lot of educational research with teachers at different schools and districts, and then teachers within that district, and so it's just like these little nested groups within your other groups. So it kind of throws off your data, and you have to recognize when you have a nested design to account for that. Otherwise, you'll have a lot more variance than you would potentially have if you knew that you should use a nested design.
So it's like the example you gave with the cottages. So that's like a variable that the person didn't account for in their research design, but that ended up affecting the outcome, was like what cottage people were in. So basically, instead of being like, all right, well, whatever, my whole experiment is messed up now, screw this, like you can do a nested design to control for the differences that occurred because of which cottage the people were in. And then once you do that, you can look at what you really wanted to look at, like whatever variables you were interested in, once you control for that effect.
So is this something you would do after?
Yes. So it's like kind of like a, oh shit, kind of analysis. Yeah. You could, but you could. Like if you wanted to control for the teacher, like if you were like, oh, I think there's going to be differences, like looking at a school in a low SES area versus a high SES area on school violence or something. Mm-hmm. There might just be inherent differences, individual differences. But so you could use it beforehand, but it's also good for like if there's a variable that you were not accounting for, and then all of a sudden it ends up messing up your results. Then you can be like, oh, okay, I need to fix this.
Yeah, I guess you can't know everything.
Yeah, because you're not going to know everything that's going to affect your experiment. You'd like to, but not always possible.
And you talked about random effects versus fixed effects.
Okay. Yeah. So fixed effects is like, if something that you were expecting. So like, I don't know, something you would put into your design that you were going to control for, or and then the nested design is something more like the cottage, where it's a random effect that you weren't planning. You weren't planning for it to. So that's all that means.
Yeah. So maybe if you knew beforehand that you're looking at kids in the school and you know which class they're in, so you would know that beforehand.
Right. And you could control for that beforehand.
Let's say that before the study you realized this could be a compound or it could affect your experiment, and you decided to control for it. It is not random anymore?
No.
It's then fixed.
Then it's a fixed effect.
Okay.
Because you've identified the confound beforehand.
So most randoms, I'm just trying to think about it. So most random, you'll figure out at the end, like that was a random effect.
Right, you'll be like, what is wrong with my data?
Okay.
And then, and then hopefully you can figure it, if you can attach it to a specific thing, like the cottages, like, oh wow, all these people were in different cottages, and, people in cottage 1 did really well on this measure, and people in cottage 2 did really bad on it, and I don't know why, but that's what happened. So then, after the fact, you would control for which cottage they were in. You'd add it as a covariate or whatever. So.
He doesn't have treatment by blocks. Did you guys read about that in the book? Treatment by blocks? I think that's used.
Is that on here?
It's not on here, but
Or is that on the text?
I think I saw it. So, what's that part of the book?
Well, it's like all they have to know is that's just like a way of
It's another
nested design or a type of random effects design.
Yeah.
Yeah.
But that's another way. It's a way to reduce within group variance.
What was it called again?
Treatment by blocks. So say that you find a lot of variability in one of your factors. So say one is like, I don't know, let's use one of his, like blood pressure or something, like huge differences in blood pressure with your sample. So you want to maybe break that down into blocks. So like this category. So you want to categorize it instead of having a continuous sort of thing. You want to categorize it so that you're kind of reducing the variance. So you're blocking it. So that's treatment by blocks.
Right. So you might have low, medium, high, or something.
Yeah.
Instead of just having it as a continuous variable, you can put people in sections, and that'll reduce your, that'll make it that instead of like that or something.
Okay, and I think we're good with that.
Yeah.
So partial versus complete omega squared and eta squared. So that's looking at the effect size, the magnitude of effect. How big is this effect that I'm looking at? How important? And the difference between partial and complete. Do you guys remember?
So that partial is not the one that includes the within group variance? The error? No.
It is the one that includes the error.
Yeah, partial includes it.
It does. So does complete, though. Complete includes all the variance. So you're comparing the effect size of the effect of whatever, like one effect, comparing that to all the variability in the experiment. So that's
between
the
group
complete.
and with one group.
Yeah.
Yeah.
So that's the complete omega and eta. And partial just looks at that effect size versus the effect plus error.
What's the formula for the partial? So it's effect plus error.
So that's the partial. The complete would include in the denominator the effect size for the other IV, for the interaction, all the effect sizes for all the variability in the denominator. And the partial just includes the specific effect plus the error.
And that's the mean square error, which is the within group variance, so the individual differences. Does that make sense? So this is more specific because you're just looking at the effect and the individual differences within that effect. And the whole one, you're looking at the effects, but then you're dividing it over everything. So it's like going to be a big,
Sorry to do the question, but when you say the effect, is that what is that?
like the, so like if you have your source table, say like the SS of A, the SS of B, so it's like whichever one of these, it could be A or B, or whatever.
Interaction.
Thank you.
Yeah, it could be the A times B. Yeah.
Whatever you're looking at specifically.
Yeah.
So if you were to assign these factors, like, okay, gender, age, and then that interaction. So gender accounts for, 30% of the variance in the total treatment. Gender accounts for 30% of the total variance. You would say that if you're looking at the complete omega, because it's the total variance, the portion of the total variance. It's not really a good way to say it in English for the partial effect.
Yeah. But
don't they do like the large, small, medium or something?
Yeah, it's for comparisons. Okay. Usually partial. You have all your partial effect sizes, and you can see which factor or interaction had the biggest effect in comparison to each other. I think is
right. Yeah.
how you would get it using SPSS.
so on your output, like it has like have we done the ANOVAs where it has like the how do they label it? Like is it part or partial or whatever? We haven't done that yet.
We haven't gone over that. That's
Okay, never mind. Yeah. I'm just trying to think of a visual way to think about it. Just basically know this. That's really what he's gonna want. He just wants you to know that it, instead of dividing it over the total variance, it's dividing it over the effect plus the error. It's the partial one. That's all he wants you to know. So just know that. And you'll understand more as we go on.
Eta is an SPSS, but the difference between that and omega is Eta is more describing your actual sample, and omega is, when you're trying to look at the population or interpret that for the population.
Right. Yeah. So the omega is kind of better, but unfortunately SPSS doesn't really use that for some reason. So
yeah, it's a little more accurate.
Yeah, a little more accurate if you're trying to generalize your findings to like the population.
Can you say that again? Omega is.
Omega is when you're trying to generalize to the population what your effect is, and then Eta is more of a descriptive term
for your sample.
Describing your sample.
Good to know. I was trying to talk about this in the homework group. It's just like, it's really like pretty, I don't know.
You said something good.
Did I? Yeah, I know. I'm like, I talked about this before. And I
you said that as the effect goes up, the power goes up. That's like
right. Yeah, like relating it to effect size.
Yeah.
Yeah. So like the bigger the effect of your interaction, so like bigger your effect size, like if it's like a large effect or something, the more powerful. Yeah, that's really it. It's not too complicated. It's just like power of anything else except of the interaction. Does that make sense?
So is this the same kind of power when we're talking about sensitivity, or this is?
Yeah.
It is? Okay.
Mm-hmm. Right. It's just as related to the interaction. I have some formula written here. I don't really...
What does it mean to have a large interaction?
Well, it's not having a large interaction. It's that your interaction has a large effect. So it's it's explaining a lot of the reason that the clinical significance is occurring. Yeah.
So we should go over what to do when you're doing analysis. Like, okay, so you found your omnibus F to be significant. What would you do next? You would look for interaction first. And if there was an interaction, you could break that down and look at maybe interaction contrast. You can look at, any other effects that you think are significant depending on your study design. So the simple comparisons, simple effects.
And that's all if you don't have an interaction?
If you do have an
interaction, yeah.
Because even though you might have an interaction that's great, you might not know exactly still what is going on between the different levels.
Right, you might still have to break it down.
Where the real differences are. He had some stuff on the, examples on the board of a couple things, and so you would know there's an interaction, and these are probably different, maybe using error terms, but are these really different, or so you want to break that down a little bit more.
If there is an interaction.
Because across this IV, the different levels of this IV, this is changing for the other IV. This is a different effect.
So necessarily don't have to cross.
No, they should not be parallel.
Right, not parallel. Sorry, yeah, just not parallel, yeah. Because if they're parallel, right, nothing's changing across the different levels. They're just going parallel.
Can you show me what another interaction is? Just two lines? Or just
so
one on top of
just
the other?
like that or something, or like that or something. Sorry, if they're straight, it's really hard to draw straight lines. But so you know, you can see like this is not changing as this goes up in the same direction at the same rate. You know, so it's all the same. Like this one might be a little lower, so you know, but they're not affecting one another.
Mm-hmm. But there are effects.
Right, but there are effects.
Okay.
Exactly. They're different lines, but they're not the way that they're going on the graph is not affecting one another.
Okay.
Okay, so what if your interaction is not significant?
Look at main effect.
Yes.
Yes.
Look at main effects. Did he give you guys a flow chart for this semester? No. Okay. So
let's see if I have it.
you look at your marginal means for main effects, and if you find a difference there, great. You can look at that and say that all the variance is accounted for by this effect or that effect. But if you don't find, even if those aren't significant, then what would you do? You're a little bit screwed. Because there's no interaction, there's no main effect. You would want to look at the power of your experiment to see what was wrong. Did it have enough subjects? Did I just design it improperly? You know, what happened? So power analysis.
Definitely.
So, so we start with the omnibus. And actually, interaction. So omnibus S significant. Yes. Look at the interaction. Significant. Yes. Look at, simple effects, simple comparisons, interaction not significant, then you do main effects. And if it wasn't significant, then do power analysis. And then, if it wasn't significant up here, you might also want to just do power analysis.
Yeah. Does that make sense, people?
It's really helpful, actually.
Really you had a handout for this.
Now that you draw it, I'm like, oh yeah, I remember that. You didn't.
Yeah, it helps you see what the function of all these are.
Right.
In the overall.
Yeah.
Like
At what
why?
point in that flowchart do you check for homogeneity?
Everywhere. I mean, you're testing if your omnibus is distributed okay, and then interact. So, like basically,
you would do probably initially.
Mm-hmm.
Look at your data.
Yeah, you do it initially, but when you get down here, if if you're just looking at a certain level or something, you might need to, like, say you violated your omnibus F, homogeneity was violated. Then once you get down here, you might calculate a new error term and then recalculate your homogeneity of variance based on whatever the effect or comparison you're looking at.
Okay.
Okay, so that's the end of that list.
I have one more question. So if you did find main effects, then you would do just more stuff, breaking it down?
Oh yeah, you could break it down also here.
Yeah.
Okay.
Depending on how many levels you had.
Okay.
Right.
Just go there, yeah.
You could, yeah.
Draw my arrow.
Sorry. Yeah, you could
do
definitely
that
do that
if you want.
depending on the level. Like if you have 3 or 4 different levels, then you could do simple effects and comparisons on that.
So specify maybe the source of the effect for all these.
Mm-hmm.
So we don't look at homogeneity variance only for interaction contrast. You can do it throughout the study then.
Yeah, and you should.
Okay.
Yeah.
It's going to actually calculate automatically with
Yeah, you just click the button and it.
Remember the little
Yeah.
games on
I like
there?
clicking
Yeah, very nice. So, but if you have to recalculate it, you might have to do that. If you have to recalculate your error term,
Yes.
you would have to do that by hand.
And how would we know that for the simple effects, for the simple comparisons?
So it's more just like if your omnibus F homogeneity variance is violated, but then you want to look at something smaller, like a simple effect or a simple comparison, then at that point you might have to recalculate your error term.
I think that's it.
Yeah. Good. Any other questions? Okay.